So far we had discussed the motion of a charged particle in a magnetic field. First we discussed in uniform magnetic field, and then we talked some cases of non-uniform magnetic field. And now our next task is, if you have a current or current element and there is a magnetic field, how much force will be exerted by this magnetic field on the current element. So, we start with linear current elements. So, the current is on a wire or on a line. Let us say this is a line, and then there is a small part here. It has a linear charge density, that is lambda. It can be a long wire carrying a current, and this charges which are moving, it is not the net charge density. Remember, in a wire, if the current is going, only the free electrons are moving, and we are talking of the charge density of only those charges which are moving. So, if that is lambda and these charges move with velocity v, then the current will be lambda times v. And how much is the total charge here in this? The total charge here is, if this is dl, then the charge dq on this small dl will be lambda into dl. Lambda is the charge per unit length, linear charge density is charge per unit length, multiply by this length dl, so that you get this charge. Now, if there is a magnetic field B, some magnetic field B exists here, then the charges are moving, and because of that you will have a force. So, force on this much charge, this element, on the element dl is df equal to charge v cross b, and that is charge is lambda times dl, and then v cross b. Now, lambda and this v, lambda times v is the current, and this we can write I, but we cannot put a vector sign over that. So, the direction of current is same as the direction of this dl, current is going this way. So, the direction of I is same as the direction of dl. So, we will put the vector on dl. So, this we will be writing I, capital I, small I, whatever. So, I, and then dl, and the direction of velocity is the direction of dl, that is positive charge we are assuming, but if it is not positive, does not matter, and the same equation will work with lambda negative, and cross b. So, that is our basic equation for force on a current element due to a magnetic field. If you have a extended circuit, then for each dl you can find the force, and then you can calculate how much is the total force. For example, if you have a current loop, suppose you have a current loop, current is going on this loop, then the total force because of the magnetic field on this current, we can integrate this. So, F is equal to integration of I dl cross b. So, a current I is going here, we take dl here, then we take dl here, then we take dl here, and so on. For each of, for entire circuit we will divide it dl, and for every dl we will calculate I dl cross B, and this whole thing summed up integrated will give you F. Now I is same, your dl is here or here or here or here, here, I is same, I can take it out of the integration, dl cross B. Now this B, if it is uniform, if B is uniform, same everywhere, uniform magnetic field same everywhere, then this also can be taken out, and then this will be equal to I integral of dl and then cross B. What is this? What is integral of dl? dl vector plus 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 dl vector. So it will be 0. If it is a closed loop, then it will be 0, and therefore it is 0. So a uniform magnetic field will not exert any force on a current loop, but magnetic field will do something to this current loop, and that is it will exert a torque, it may exert a torque on this current loop. The net force is 0, the net force is 0, but net torque may be there. Just like if you have say some rod here and apply a force here, apply a force here, same amount, the net force is 0, but there is a torque. So similarly, on a current loop you can have torque. In schools we generally take a rectangular loop, and then the magnetic field is there, we turn it and calculate this force on each of the 4 arms and then calculate the torque. So we will go slightly ahead of that, and we will start with any general plane loop, not necessarily rectangle but plane loop. So let us say that it is in xy plane and it can have any shape, and then it contains some current, and then there is a magnetic field, general magnetic field. B is say Bx I cap plus By j cap plus Bz k cap, and we want to calculate the torque by this magnetic field on this current loop. So again we will take some small dl and then start with there. So let us say this is our small dl, this is our small dl. So what will we do? We will write force, first we will write force on this dl, force on this dl, and that will be as we did here, I dl cross B. So I and then dl and cross B. Now this dl you can write as dh. So this is force, and what is torque? What is torque? Torque of this force about the origin, very important. When we ask what is the force on some object, we don't care where the origin is, but if you ask what is the torque, then you have to tell where the origin is or about which point the torque is needed. So here we are taking torque about the origin. You can take this anywhere, and the magnitude of torque, the direction of torque will not change. It is independent of the origin. Why? Under what conditions? If the net force is 0, if the net resultant force is 0, then the torque is independent of origin, but if it is not 0, then the torque depends which point you have chosen to calculate that torque. So, here we are choosing origin, but we understand that since on a closed loop the net force is 0, the net force is 0. Therefore, even if you take origin somewhere here or here or there, it will still be the same. So, we calculate it about this origin. So, what is that torque d tau? What is that torque d tau? This tau I have used for volume also, d tau for small volume element, but I have put a vector sign, so it cannot be volume element. So, this is for torque. So, this will be r cross f, r cross df. That is the definition. That is the definition of the torque. And what is this r? From the origin to that object on which the torque is being calculated. So, this vector is r vector. This vector is a position vector, and this df is the force which is acting on this element here at the position r. So, it is this. So, this will be equal to r cross df is I, df is I, and then dl, and cross b here, and you have to put the bracket here. There are two cross products. So, it is not associative. It is not that either you do this cross and after that you do this cross, or you do this cross and then this cross, they are different. So, df is this, r cross df, for df we write this. So, this is I, and then r, and then cross, and then dl, and then cross b. So, it is this. Okay. Now, to simplify this, remember this relation A cross B cross C. In elementary vector algebra, you must have done this. It will be A dot C vector B and minus A dot B and vector C. Okay, this is an identity. You can prove this very well if you just take origin x, y, z axis, write in components, you can do that. And to remember, this B, the first vector in this parenthesis, in this bracket, is to be taken out, and the rest two are dot products, and then minus this has to be taken out, and the rest two are put as dot product. Use this thing here. What is this? R vector cross dl vector cross b vector. Use this. So, our torque d tau is equal to I, and then this has to be taken out. So, r vector dot b vector, r vector dot b vector, and what is taken out? This dl vector, then a minus, then this b has to be taken out. So, r dot dl, r vector dot dl vector, and then this b which comes out. This is it. All right, this is it. Now, we have to integrate. We have to integrate. So, the torque will be I times integration of this entire thing. So, integration of r dot b and then dl here, and then minus integration of this r and dot dl here, and then b here. And remember, we are talking of a closed loop. So, this integration does not have a lower limit and an upper limit. It is this part plus 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 this part. So, this is a kind of closed loop integration. So, we put this circle here to tell that this is a closed loop on which this has to be integrated. Now, if you write in component form one by one, let us look at this. Integration of r dot b and then dl vector. What is this? This r vector is x I cap plus y j cap. This r vector. What is this r vector? Remember, come here on this figure. Here is the origin. This is the point where we are, and this is r vector, and this is in xy plane. So you can write it as x coordinate I cap plus y coordinate j cap. So it is this r dot b. R dot is this. Then dot. What do I write? bx I cap plus by j cap plus bzk cap. It is this vector, and then r dot b and then dl, and dl vector is itself. What is dl vector? This is dl vector. What is this dl vector? This is x comma y, then this is x plus dx comma y plus dy. So this vector will be dx I cap and plus dy j cap. Can we do something? Can we do something? Integration of dot product. So it is x and then bx. I dot j is 0, I dot k is 0, then j dot I is 0, and then j dot j is 1. So plus y and then this by. This is this part, this is this part, and then you have dx I cap plus dy j cap. Now this is what? Let us take this one. So you have x bx dx, this is one part, x bx into this dx, and this whole thing is on I cap, this much I cap. I am only writing this and this I cap, and then you can start with here also. Yes. So plus integration, this integration y by, and then this dy, and this whole thing j cap. Okay. Once again, I am opening this bracket. There are two terms here, there are two terms here. So you will have four terms. So those four terms I am trying to write. So this is x bx I cap. Then we have written this y by j cap. What is left? The left thing is x bx and then this dy j cap, and then plus here. What is this thing? This thing is, what is left here? This one is left, right? This one is left. So integration y by and then dx, and this is I cap. Lot of algebra, but simple algebra. You can just do step by step and you get this. Now there are several integrations. This one, this bx is constant, this bx is constant, so it will be x dx integration. So let's name it 1, 2, 3, 4. So let's talk of one. Let's talk of one. What it is? Bx integration x dx. Bx is constant, comes out, integration x dx, and then I cap. So this is I cap. Let's do the integration. Let's do the integration. We'll put the I cap later. What is this? X dx on a closed loop. What is this? This is 0. X dx, if you do, x dx here, then x dx here, x dx here, x dx here. So, for this x, for example, here is this dx, but for the same x you will come here and there will be a dx in this direction. These will have opposite signs, same x, but dl is this way and here dl is this way. So, when you do this total integration, this will become 0. So, x dx integration is 0, the first one is 0. Similarly, y dy, the second one, this second one, y dy, this is also 0, this is also 0. B y, integration y dy, this is also 0. 3 and 4, so 3 is, what is 3? 3 is bx, you can take this bx out, x dy j cap, x dy integration, and this is in j cap, and fourth one is y dx, by comes out, and then you have y dx, and that will be with I cap. This will go with j cap, this will go with I cap. What is this? You must be familiar with this y dx integration. Okay, if you have a curve y here and x here, and this is, let us say, at x this is the y, this is x and this is y, and then you proceed little bit ahead and this is your dx, and then you reach here, then you reach here, and this y dx is essentially this area under this curve, this much curve, and as this dx tends to 0, this description is better and better. So, this y times dx is this area. So, if you go from say this point to this point, a to b, then you add all these areas, and that is the definite integration. But here I have a closed loop, here I have a closed loop, and this is how we are going on it. So, what is this y dx here? For this particular x, you have a y dx here, and then for the same x you are also going to get this y. So, you are going to get this y1 here and y2 here. So, 2 times it will be y dx, one will be y1 times dx, other will be y2 times dx, and here x is increasing, so dx is positive, and here this arrow comes like this. So, here you are coming this way, so x is decreasing. So, this will be negative, y2 times dx will be negative, because y2 is here and dx is on the left, whereas here dx is on the right. So, y1 times dx will be positive. So, this taken together, these two taken together, it will give you a negative value, and same is true for any x, this x, this x, this x. So, when you do this entire integration, you are going to get this area, okay, area of this curve or this loop. Why? Because here it was y1 times dx, and here it is y2 times dx, and y2 and y1, y2 is greater, y1 is smaller, and dx is opposite sign. So, you have to subtract from this y2, you have to subtract this y1, and you will be left with this times dx. So, you are getting area of this whole curve, this one. So, this is equal to by times the area of this curve, and a negative sign, and fourth one is with I cap. So, it is I cap here. Similarly, this third one x dy also you can do, you have to do it this time this way. So, this is y somewhere and it is coming like this. So, your dl is this way, this is y, dl is this way, this is y, dl is this way. But with the same y, you also come here and then is this way. once again you get the same area. Once again you get the same area, but this time with a positive sign. You can work out where are you going and how the dy is changing and all that, and you get this as bx times a, bx times a with a positive sign, and the third one is coming with j cap. So this is j cap, this is j cap. So this thing, integration r dot b dl, this is equal to what, 3 and 4. So bx a we can write outside, a we can write outside. So bx times area that we have written, and then j cap, and then minus here and by k cap. So this is r dot b dl equal to 1 and 2 are 0, 1 and 2 are 0. Then this 3 is bx, so this bx, and then x dy is a, area, so that area, and then j cap, so this j cap, and then this one is minus by, this one is minus a by, so minus a by I cap, so this is I cap. Okay, what we have done? We have only done a small part of it. This one, we have only calculated this one, that r dot dl is still there. R dot dl is still there. So let's do that. Let me make some space here, and now our task is this one. So integration of r dot dl. This b is constant, we can keep it here. So let's calculate this. What is this? What is this? R is x I cap plus y j cap, and then dot dl is dx I cap and plus dy j cap. Okay, integration. So is dot product here, I cap, this will be integration x and here dx, this is 1, j cap, this will be integration y and dy, right. This thing with no I cap, j cap, that's it. And I cap dot j cap is 0, j cap dot I cap is 0, so it is just this much, and this is 0, this is 0. On this entire loop, x dx integration is 0, y dy integration is 0, and so this is 0. So this part is anyway 0. So let us come back to the torque. We are trying to write this torque. So this torque is equal to I here and then this, and how much is this? R dot b that we have calculated, it is here, r dot b dl is here. So this I, and then for this we write a and bx times j cap minus by times I cap. It is this is the torque. Can we do some simplification or beautification? Let me give it a try. It is a, and then let me write it as k vector cross bx here, and I have to bring j. So let me write I cap here. See what happens. K cross I, k cap cross I cap is j cap. So this is j cap. This bx is here, IA here. So this term is fine. Next term, let me write this as by, and let me write this as j cap. See what happens. IA is here. K cap cross j cap. K cap cross j cap is minus I cap. right? In cyclic order you have I, j, k, I, then j and then k. So, I cross j is k, j cross k is I, k cross I is j, that is how it will go. And here it is k cross j, opposite. So, this will be minus I cap. So, minus I cap is here. So, this minus I cap I can write as k cross and then cross product with j cap. It is this. Since it is k cap here and I am making the cross product, I can also add anything in k cap direction. K cap cross k cap is 0. So, what do you get? I, A, k cap cross B. Torque is equal to I area k cap cross B. Simple, short, cute. And this A k cap, remember this loop is in xy plane. This loop is in xy plane and there is an arrow, this arrow. So, if I take the area, magnitude of area from here and then put a unit vector in the perpendicular direction, you know this is called area vector, right? Area vector corresponding to any given area. So, if it is a plane area, very simple. So, you just take the perpendicular, the area vector will be along that perpendicular and magnitude will be equal to the actual magnitude of the area. But then perpendicular could be this direction, perpendicular to be could be opposite direction. Which one? This arrow will decide. Seeing from this side, it is anti-clockwise. This arrow tells me that you have to traverse on this loop in anti-clockwise direction and then the area vector is towards me. If the arrow is opposite and if it looks clockwise to me, then the area vector will be going away from me, that means will go into the board. So, this A and k cap means this is x axis, this is y axis, z axis is perpendicular, k cap is unit vector towards me and therefore, this A k cap can be written just as area vector A. So, this is the torque, this is the expression of torque. If you have a current loop, find out what is the area, put proper vector sign perpendicular to the area, clockwise or anti-clockwise accordingly, and then cross B is the torque on the current loop by the magnetic field. So, we will stop here today and do more calculations next time.